Zeus. It's curious. Zeus, go.
Sorry.
Ready? Ready. Alright. The math behind basketball shoes and how it relates to engineering by your host, Cameron Robinson. Alright. Math and engineering are an important part of everyday life, and the things we enjoy in sports like basketball have so much math behind how things happen, and every scenario in math can somehow be applied to that. And at some point in one's life, learned about Newton's third law, Newton's law. They'll never know how much that applies to. So, people may think it's just a concept that kids will understand, but it's not really going to be applied in the outside world. But it's applied to many other concepts, and it's crazy how music has gone from an apple falling out of a tree on its head to all of the different things, new ideas, what would you say? Alright. So basically, the inspiration behind this project was the comparison of two basketball shoes. So, how engineering relates to the outside world and things I enjoy day to day. So, the Kobe 6 Grinch, which is the Christmas time, but it's basically a really good basketball shoe that a lot of people wear when they play basketball, and so a lot of technology is embedded in the shoe. As you can see right there, there's like a whole air pocket that Nike's known for, and then their heel padding and their foam to make it more comfortable, and basically allows Newton's third law to take action when you jump off the ground. And so basically, in traction as well. So all of this may sound like hot air, but then Newton's third law can explain how this shoe is different than another shoe that wouldn't be as good for playing basketball, but like a Converse platform shoe. So they're not considered basketball shoes at all. And instead of like the Kobe, it's like a brick on your foot. It doesn't really do anything other than get you taller. It's like just a whole filled insole with nothing really there to cushion you. And so that's why Newton's third law, it explains how when you apply force to something, it will give an equal and opposite reaction back. So if let's say I'm pushing force on the ground, and that ground is going to return force as I jump up into the air. And so that's how these shoes with the padding and foam can help with that. And then it can influence it in these different equations and account for the changes like physics does. So, bring us on to the next one. So after all the talk about it, let's talk about Newton's third law. Newton's third law states for every action, there's an equal and opposite reaction. So for example, if you like punch a wall, if you punch really hard into the wall, that wall is going to return the force and then it's going to hurt your hand a lot. It's not just going to like go through the wall like you're phasing through it. So that's basically what Newton's third law is trying to explain with this picture. So when you push on something, it's going to be an A reaction, and that B reaction is going to push back on you. And so basically, like if you're playing basketball and you want to jump, as I said, those different shoes, if you're wearing the Converse shoes, you're really just not going to jump that high because it's basically just going to be you pushing like a harder thing on the ground, then you're not going to go up that high, and it's not like a lot of cushion. So the difference between those basketball shoes is that cushion or no cushion. And so those shoes determine how high you go based on Newton's third law. So now brings us to the applications in engineering. So these maths, such as calculus and differential equations, pi is always 3.141592653, or Euler's number is always 2.71828. But in physics, these problems have so many different constants and changes that are happening in the equation. So which is why so much math goes into building things like this house and the structure that have to account for many different changes in the weather, the area. And so it's not like a Lego set when you have your instructions just like piled out in front of you and you just do this. There's a lot of different mechanics and changes going into it, which is why physics is such an important part of this world and basically the everyday life that goes into it. And so that's also why Newton's second law of motion is so important to that engineering field, because it accounts for those changes and is basically the base for all equations that base around it. So in calculus differential equations, pi is always 3.141592653, but Euler's number is always 2.71828, or even Avogadro's number as it relates to chemistry is 6.023 times 10 to the 23rd. And in chemistry, you need to understand the bond and physical attributes of the materials you're working with, which is why it goes so hand in hand with physics and calculus, because that's how you build things, that's how structures are built in the real world. So now it gets us to how how this is represented, how this is implemented. So some of the easiest problems to solve include the base formula F equals ma from Newton's second law, which is force equals mass times acceleration. So if somebody's trying to figure out how much force they need to push like a car or something, all you need is the mass and acceleration. So if the car weighs 1,300 kilograms and you're trying to push it like 5 meters per second squared, then all you have to do to find the force is multiply those, which gets you 6,500 newtons. So you need 6,500 newtons of force pushing that car if you wanted to get it to 5 meters per second squared, based on the weight of the car. I mean, miles per
How
hour.
much acceleration do you need?
I mean, if it's dead in the road and you push the side of the road, I mean, like 10 miles per hour, like you're pushing the car.
You're applying force.
Exactly, so that the car applies force back on you, which is why it's hard to push it. So, yeah, well, that's why I put 5 meters per second squared.
So the car is applying force back on you. What other forces are at matter that have a constant that you have to worry about?
I mean, obviously, like gravity.
Right. So it's really just overcoming gravity. That's the acceleration. That's why that acceleration that you need isn't so much an arbitrary 5 meters per second squared. It's actually equal to or greater than the force being exerted on it downward, which is
9.8 meters per second squared.
correct. So that's what should be in there. So you'll have to adjust that as well. Right. And you understand why that's the case.
Yes.
Okay.
So, this will only be like a basic level problem though, which is why this new class I'm going to, calculus of physics, goes hand to hand to solve these different types of real life problems in like labs. And so like, if you're trying to solve a problem with Formula 1 car and trying to reduce air friction and drag, that's where these more in-depth concepts apply to engineering and solving graphs and trying to figure out how much you need for like an air flap in the back, so that way you can slice through the air and you're getting more acceleration in a Formula 1 car. So from there, that's when you apply all these harder level calculus concepts, and that's how physics calculus go hand to hand, making these different cars. And so that's why MIT is such a great place, because they have all the funding that you need for these crazy ideas that you have. And then when you try to make an idea like that, then you can execute it based on whatever idea you have, and then you can build it, and then they'll execute that for you. So it's like super cool, all these different concepts that you can make. Also, so let's say this problem, the car weighs 1,400 kilograms, it needs to be an acceleration of 20 meters per second squared, overcoming the force of gravity being applied at 9.8 meters per second squared. And then all you need to do is F equals ma, so F equals 1,400 times 20, but you get 28,000 newtons. So you need 28,000 newtons of force to achieve that goal. Alright, so basically what I'm trying to say is that physics, or like all this stuff, can be applied like pretty much anywhere in general. Like everywhere you look around you, physics or engineering or some sort of math has been applied. You don't take a step without noticing that, which is why I've been like figuring out how things work. And when you take steps and you look at people, even like taking steps, that's applying some sort of engineering law. And so that's just why everything is so cool in engineering, and like all these things that you enjoy, like I said, playing basketball, watching TV, all this engineering that goes with it. That's why I like to think of like calculus and physics in real life, because physics is basically just calculus but being implemented everywhere. That's why there's so many cool opportunities with these physics, and go back to simple things like Newton's second law, third law, derivatives, integrals, and all of those base concepts can go hand in hand with things like delta, which is the change, counts for the change and everything. So that's why I've been, like the email you sent me, I think about the characteristics of a day-to-day basis that I want, and like MIT is everything, literally, and there's so many great opportunities. Getting head starts on this is like pushing me to be able to achieve that opportunity, going to MIT grad school when I'm like 17 or 18. And so that's why basically all these concepts and applications that I've explained can be taken to new levels. That could be the one taken to that level. So that's why all this is so important. Ooh.
Why do integrals matter here? You're talking about their opportunities with physics, and it relates back to simple things like Newton's second and third law. What's Newton's second law?
Second law, so it's like basically F equals ma, and the net force applied on a body, so force times mass times acceleration.
And third law is?
That's the equal and opposite reaction for every action.
Okay. Integrals are what?
Integrals are like the area under a curve.
Right. Which is not a simple thing.
Well, you wouldn't think of it as a simple thing, but when you think of calculus, that's like the face of calculus, integrals, derivatives, and all of those can build on different things and higher equations that you go to. So like just take an interval of like x squared would get you 3x over 3, but basically, or x cubed over 3. But you can apply that into so many more higher up equations, and then, so basically integral is just like one hard thing that you can learn, but then you can use that as a stepping stone for harder things to learn, and you can build stuff with that.
That's the right answer.